Okay, good morning or afternoon. Again, we are here today for the real gas behaviors lecture. Specifically, in order to accomplish the lab goal, we're studying what's called the van der Waals equation. So real gases, we've been studying ideal gases in chapter 5, but real gases deviate from the ideal behavior described by the ideal gas law. So real gases deviate from, quote, ideal behavior. Okay, under two conditions. These two conditions are when the temperature is very low and or when the pressure is very high. So aside from these two sort of unique scenarios, gases behave according to the ideal gas law, where PV equals nRT. But when you get really, really cold, we're talking just a couple of degrees Kelvin, or to really high pressures, and that varies from one gas to another, what it considers to be high, we start to see some abnormalities developing in the behavior of a gas. And so there's two specific things that happen. All right. One is that the volume is affected. Okay. And the second is that the pressure of the gas is affected. Okay. The volume is going to become affected. We can think about what life is like as a very high pressure gas. At very high pressures, you have a lot of gas particles crammed into a small space, is one way to cause that condition. All right. And at that scenario, you know, imagine the walls of our room shrinking down and getting smaller and smaller. There's so much freedom between all of us right now. But as the room got tighter and tighter, right, we would get closer and closer together. And that postulate from the kinetic molecular theory that says that gases have a lot of space between their particles, that goes away. All right. And in that instance, the volume that we occupy, or the volume that the gas particles then occupy, becomes a significant value, not something we can ignore anymore. All right. And so we have a correction, a corrective factor, all right, that would say that the volume totally occupied by the gas is actually a little bit bigger than the ideal volume would predict because of the gas particles themselves. Right? You can sort of imagine them bulging out like the container a little bit because of their volume. All right? So the volume is actually increased due to the particles. Okay? So in ideal gas behavior, right, going from PV equals nRT, the ideal volume of a gas would be nRT divided by the P, the pressure. But the real volume will be the nRT divided by P plus N moles times B. So B is a corrective factor. Okay. So B accounts for basically how big the particles are, depending on what gas you might be working with. It's a really small value for monatomic gases like helium, all right, or argon. But as you get to larger, more complex gas molecules, in lab today we're working with sulfur hexafluoride. A molecule of sulfur hexafluoride will dwarf a helium molecule. And so it, of course, takes up a lot more space, each one of those molecules. All right? Now there are several different versions of attempting to model real gas behavior. This version is what is called the van der Waals equation. All right. There have been several. This was one of the earliest ones that successfully predicted real gas behavior, but the more sophisticated models have been developed since. But just to give us an idea of what's going on with real gases, I want to talk about the van der Waals equation. Okay? Now, pressure. The pressure of the gas would also be affected. One of our other assumptions in the kinetic molecular theory is that the particles have essentially no interest in each other. Two gas molecules just zoom by each other, right? Or if they do hit each other, we called it an elastic collision. They're just like two pool balls, bounce off each other, and they're gone. But at these conditions of high pressure or at very low temperature we now know means less energy. Less kinetic energy means the molecules are moving slower, so they're not behaving like these hard billiard balls that we've imagined on a pool table. They now start to behave more like softer, squishy materials, and when two molecules collide, they kind of stick for a second. All right? And when two molecules pass each other, instead of just zooming by, it's kind of like they kind of are slowed down, like to look at the other molecule is one way of imagining what's happening here. All right? Whereas if they had a lot of space, they wouldn't be able to see each other or pay attention. But when you cram them in, like if you were in a crowd, right? You can't walk the day after Thanksgiving if you go shopping, right? You can't walk in a straight line to the object that you're interested in. You have to weave your way through a crowd of people, and that's going to take longer. The effect that this has in a gas on its pressure is the net result is to decrease how often the particles get to collide with the walls of the container, because they're colliding with each other a lot more. And they're sort of sticking temporarily to each other. And they've got to get through the crowd in order to get to the walls. So the effect here is that the pressure is decreased due to sort of the, if you want to think of it as the congestion. Okay? But it's most strongly due to what's called the intermolecular forces. Something we're going to study in chapter 11, so I can't go into it in too much detail right now. But that's the idea that when two particles pass each other, they kind of slow down to see if they are attracted to each other. And do they want to stick to each other? All right? That's what the intermolecular force would be. Okay? So in the ideal gas law, our pressure would be nRT divided by V. In the van der Waals equation of state, it's nRT divided by V, and again with a corrective factor. We're subtracting A times N over V squared. And so A is a